to the lecture series in computer science on principles of deep learning. In today's session, we are going to focus on Tanh and ReLU activation functions. And in today's session, we are going to know about the introduction to Tanh and ReLU activation functions, their features, different applications, and how these functions can be implemented in Python. In previous session, we have discussed on sigmoid function. Usually in activation functions helps whether a particular neuron can be on or off. So, there are various activation functions we come across in previous sessions, and today's session focus mainly on about the Tanh activation function. So, it is a hyperbolic tangent activation function, and the values that ranges, the output ranges between -1 to 1, and hence the hyperbolic tangent can be mathematically represented as tan h of x is equal to sin h of x by cos h of x, which is equivalent to e power x minus e power minus x by e power x plus e power minus x. And if we see the features of this tan h function is a smooth, continuous and differential function. Unlike the sigmoid function where the output values ranges between 0 and 1, this tangent h function is a 0 centered one, which is very useful for certain type of applications. Now, moving on to the other features of Tanh activation function. We all know that it is a non-linear activation function and it is an exponential function. It is a 0 centered output function. It has a stronger gradients and it is 0 centered bias correction, and it is very suitable for multi-layer networks. Out of all these features, the very important is the 0 centered output. Here, why we are saying 0 centered output? If you see the sigmoid function, the output ranges between 0 to 1 only, whereby only one side oscillation will be there, positive. There is no negativity at all and nothing is concentrated over the 0 origin. In this Tanh function, the output values ranges between -1 to 1, where there is a 0 centered output over here in Tanh. Now, moving on to the limitations of Tanh, where we should not use this Tanh functions or this Tanh where it is not applicable. We can see here also vanishing gradient problem occurs, and here it also in many scenarios where the application requires very large input or very small input, this Tanh function cannot be applied. Moving on to the various applications of Tanh functions. These are the different domains where this Tanh is very much applicable: deep learning, data science, control systems, signal processing, physics and engineering, economics, neuroscience and graphics. Out of all these fields, where in which of the applications we can use this effectively here is, in case of deep learning, this is very much used as an activation function, we all know about it. And in case of other signal control systems, where we have to bound the signal controls, in such type of applications like saturation modeling, this Tanh is very well applicable. And in case of signal processing, where audio soft limiting or signal compression applications needs a type of clipping. So, here to prevent the clipping, this Tanh activation functions can be useful. Now, moving on to the other applications where in economics, logistic in growth models. So, here in case of these applications, you have to saturate, you have to see the trends, you have to follow, or we need to develop a model which saturates in the trends. And moving on to the neural signal modeling applications, here we need to fire the rate approximation. So, this signal modeling functions, the purpose of this is you need to find out the rate approximation. And lastly, in case of graphical applications, whereby with respect to animations, this is helps us to see the natural looking transitions. And these are the various applications where in detail these applications how they are applied in the Tanh applications we have seen these applications being applicable to various neural network architectures. Now, in case of RNNs, that is recurring neural networks, this tan H is mainly used to model the sequential data. That is, here you can predict the time series predictions and language modeling can be done, and hence it is a zero centered output. This helps us to catch both the negative and positive temporal dependencies effectively. And moving on to the LSTM networks, it is a short term memory networks, where in case of these networks tan H is very much employed in the cell state, and here the output will regulate the gate to have an information flow, and its smooth gradient helps us to mitigate the vanishing gradient problem, and it helps us to for better learning over the long sequences. So, in these two types of architectures, tan H function can be applicable. And moving on to the other applications of neural networks, in case of natural language processing, here some of the applications like sentiment analysis, language translation, text generation, in all these applications tan H will effectively process the textual data, and it deals with both the positive and negative sentiments. In case of image processing applications like computer vision tasks, this tan H is mainly used in convolutional neural networks, and this will helps us to introduce the non-linearity, which enables the network to detect the complex features in the images. And with in case of the audio analysis, whereby you are in a position to recognize the speech or any music related task, this tan H functions will capture the patterns out of the signals, that is the audio signals, and they helps us to relatively solve the problems in case of the audio analysis. Moving on to how this tan H can be implemented in Python. Till now we have discussed the tan H, its various features, its limitations, and what are the different applications where these activation functions can be applied in case of the neural networks. Now, how these tan H can be implemented in Python? If you see here, tan H is also an S-shaped graph. Here if you see the Python code of implementing, as usual we need to import the matplotlib library for visualization and numpy for taking the input range of values. So, here we are defining a function called tan H, which will return the value of sine by cos. Now, taking the x axis and y axis, the limits with -5 to 5 as x axis, and y axis is the tan H values of the x. Now, these are the other usual notations which helps us to visually showcase the tan H graph onto the screen. So, here plot is a function which will makes the pixels of x and y over the graph. We are labeling the x axis with x and y axis with tan H. The same is depicted over here, x and y axis, and now here we are giving a title for the graph, that is tan H function. The output of the title will appear here, tan H function, and taking the x axis limitations as -5.5 to 5.5 and y axis limitation to -1.1 to 1.1. We are following a grid pattern, that is to showcase these broad lines. This is a grid structure, and here plt.show function helps us to showcase the tan H function, which is an S-shaped curve. Moving on to the next example, how this tan H function can be applied in case of a neural networks. So, we are here giving only the basic details of how it can be called. So, we are importing the TensorFlow library, and within this we are following the sequential data processing. That means, sequential model is being taken over as an example here, and here we are importing one more layer called the dense layer. Hence, in order to call off the function, the model is being called with a sequential and with the activation function of tan H. Here the shape is taken as 32, and one more activation function called softmax is applied to the dense layer. Now, moving on, we are compiling the model with the optimizer ADAM, and loss is being taken as the space categorical cross entropy, matrix has been taken as the accuracy. So, if you provide these input parameters to the model with the compilation, we see that how this neural networks have been, that we have just not taken any data set to implement the tan H function, we have just taken how this can be applied in neural networks. Now, moving on to the other activation function called ReLU, it is a rectified linear unit, and this activation function mainly introduces the non-linearity to the deep learning model, and this also solves the vanishing gradient problem. Here the function is depicted as f of x is equal to maximum of 0 comma x, and here this ReLU activation function is differentiable at all the points except at the 0, and here this model is, if the input is positive, the ReLU function outputs the same value, but if the model input is negative, the ReLU function outputs the 0 value. Moving on to the graph, how the ReLU can be represented. It is represented as shown in the figure, where the x axis ranges from -10 to 10. The ReLU activation function is applied using the Python code, which we will be discussing a little later. Moving on to its future, how far the ReLU function is better than tan H, or what makes this ReLU function to be utilized in a neural networks, because of its computational simplicity, its non-saturating nature, its sparse activation, and better gradient propagation. So, these are the features which makes ReLU a popular choice. Now, moving on to the limitations of ReLU. ReLU has a dying ReLU problem. Here, if the large gradient causes the ReLU neutron to output 0 consistently, then the learning process will be stopped, and this will effectively, the process or the model will be in a dying position. So, if the large gradient causes the ReLU neutron to output 0 consistently, then this will stop learning. The other disadvantage is unbounded output. Here, the ReLU's unbounded positive output can sometimes leads to gradient exploding during the training process. So, these are the two limitations we have with the ReLU function. Moving on to the other applications of ReLU, in case of deep neural networks, it helps in image classification, natural language processing, and speech recognition. These are the three applications depicted over here, and in case of image classification, we understood that all the image classification comes under an architecture or uses an architecture called convolutional neural networks, and this ReLU helps in detecting the intricate features or patterns within the images. The main advantage is to detect the features or patterns within the images. Moving on to the natural language processing, here the ReLU, in case of NLP, it introduces the non-linearity, which will automatically improve the computational efficiency, and it is helpful for, as layer by layer, it will improve the computational efficiency. And moving on to the speech recognition systems, in automatic speech recognition systems, these ReLUs helps in extracting the important features or relevant features from an audio signal. Moving on, how this ReLU can be implemented in Python, we as usual take the NumPy library, and here we are depicting the input range values, and the ReLU function is being called, where the function utilizes either the 0 value or the x value, maximum of those. So, the output of these functions is 0.2 and 0.4. Now, how ReLU can be implemented in neural networks or in deep learning can be represented using the Python libraries as follows. See, we need to import the TensorFlow library, and we are importing the Keras libraries from the Python. Now, here we need to define a sequential model, and here in this in defining a sequential model, we are calling the activation function as the ReLU, and here the model is being again compiled, and this has been taken without any data set in action. We are just saying that what are the different parameters and what is the activation function, how many input shapes or parameters we are sending, how many output layers will be displayed. So, we are calling out or compiling the model, and we are discussing or printing here the model summary. So, if you print the model summary, the output is as follows. Here we say the model is sequential and the layer, we have applied dense layers and the output shape is being defined, and these many parameters values have been taken. And here see the total parameters is 2762, trainable parameters is 2762, non-trainable parameters is 0. So, in case of ReLU function, if applied in a deep learning networks, how the sequential model has to be activated using the ReLU function is being discussed over now. So, so far we have discussed how the tanh and ReLU functions are implemented using the Python libraries. Now, moving on to the other variants of ReLU functions, how this ReLU can be improved, what are the other types such that the function gets smoother or even better. So, we have the leaky ReLU, parametric ReLU and exponential linear unit. So, if you consider the leaky ReLU allows a small non-zero gradient when the input is negative. So, this helps us whether to keep the neurons active or not. This mainly useful to make up the neurons active when the input is negative. So, next one is the parametric ReLU, and it is depicted as PRELU, and here it learns the slope of the negative part during the training process, which provides more flexibility in getting the output. And last one is the exponential linear unit. Here it smoothens the negative part of the function, and which helps us to combine the benefits of both ReLU and the tanh. So, these are the different variants of ReLU net activation functions. Now, we will see a real application of how these three functions can be applied to any database. So, I have taken here Prima Indians diabetic database from the Kaggle, and if you see the different columns of the data set, we have the values on pregnancies, glucose, blood pressure, skin thickness, insulin, BMI, diabetes, pressure. These are the different columns. Like this, we have 9 columns in this data set, and the values of each of the individuals has been fields have been taken from the Kaggle data set. Now, moving on to how to implement this and how to view whether the performance analysis of tanh or ReLU or sigmoid can be compared, the performance analysis, we will go through a Python code now. So, as usual, we are downloading the libraries and we are importing the sequential model. We are taking the dense layer. After that, we have to load the data set. So, what is the command for loading the data set is, you need to have a CSV file of the data set, and the name of the data set is given is pima_dataset.csv, and this CSV file is separated by a delimited comma, and we are loading this text file into the NP. NP is the numpy variable we have taken, and this is being handled to a variable called the data set. Now, moving on to taking the input values and the target data, we need to take the input data how much percentage and the output data how much percentage. Okay. So, we consider here the X data set and the Y data set. From the data set, we have taken the input part and the target data part. Now, moving on to modeling, we are taking a sequential model, we are calling out the function. Now, we are going to apply all these 3 activation functions and see the performance analysis. Now, see, for the model, we are adding the first layer dense of 12 and the input shape is given as 8, and you have utilized the activation function called the ReLU. Again, for the same model, we have added the layer 8 with the activation function ReLU, and we have for the dense layer, we have taken the activation function as the sigmoid. Now, these functions has to be compiled and we need to fit the training model. See, for the compilation, the syntax that goes within the function compile is, you need to mention how you are going to calculate the loss and which optimizer function we are going to use and the metrics we are going to take. So, these three parameters will be in detail discussed in coming sessions, but for time being we need to understand how the loss has to be calculated under which function and how the optimization functions, there are several different optimization functions, in that we are using the Adam function. So, the model is being compiled now. Now, we are training the model with the input values like x and y, and epochs we are defining as 225, batch size we are taking as 25. Now, here the model is being called for fit. Now, if you execute and see in Google Colab, we understood that after the execution of 225 epochs, in case of ReLU function, we got an accuracy of 0.7785. Here the variable loss, value of loss we have taken as 0.5892, and if you see the accuracy, value accuracy 0.7143. Now, when compared to the ReLU, if you see the execution of tan h functions with the same epochs, we see the loss function as 0.5466 and here the accuracy value is 0.7003, and here if you consider the sigmoid function after execution of 225, here after these steps the loss is calculated as 0.5574 and the accuracy is maintained as 0.7280. So, out of all these three functions, we understood that if you take the accuracy, the three functions with 77% accuracy, ReLU, tan h function is of 70% and sigmoid is of 72%. So, if we see, we come across here when you see the data set over here, this is a prima Indian data set which depicts or which predicts whether a person can be affected with diabetes or not, and we have taken several different column values, and these values when you apply a model and see through the activation functions how the prediction accuracy, how much accurately these functions have been applied. If you see, we come across after execution that ReLU is performing better than tan h and sigmoid, and when you compare between tan h and sigmoid, sigmoid function gives the better accuracy. So, these will be in detail learned in the next coming sections when you understand the architecture. When you understand the architecture whether to apply CNN or the other architectures, then these functions we can compare for any data set how these functions can be applied and give the better performance. So, to conclude this session, we are just discussing the activation functions which might be useful in forthcoming sessions for solving different real world applications of deep neural networks. So, to sum up, we are discussing the various parameters, how the output range of each function will be there, is the zero centered problem is being solved or it been answered, how the gradient behaves, what is its computational cost, and whether the vanishing gradient problem is being solved or not, or the problem exists or not, we are going to see. So, taking the first feature, the output function, tan h, we come across the output is -1 to 1, the sigmoid has 0 to 1 and the ReLU has 0 to infinity. Moving on to the zero centered, we already know that there is no zero centered in case of the sigmoid and the ReLU function. Only zero centered problem is being solved in the tan h. Now, with respect to the gradient behavior, there is a smooth transitions in case of tan h and sigmoid and non-smooth in case of the ReLU function. And with respect to the computational cost, this tan h and sigmoid is moderately low with respect to the, is moderately high with respect to the ReLU, where the ReLU has a computational cost is very, very less. Moving on to the vanishing gradient problem, in sigmoid and tan h, the vanishing gradient problem exists, but there is little bit less focused with respect to the ReLU functions. So, till now we have discussed different types of activation functions that helps in neural networks, whether a neuron has to be fired or not. In subsequent class, we will discuss what is meant by machine learning and what are the different algorithms that come across in machine learning. In this way, it will be helpful whether how an algorithm to be chosen, and then which type of neural network architecture can be applied, and then which activation function has to be utilized. So, these classes forms the basics of deep learning. So, from the start we have discussed deep learning, the different types of architectures, different types of activation functions. Now, we will move on to the different types of algorithms which makes machine learning popular in the subsequent session.